So we're going to begin with section 10.1. 10.1, it's about you will be given a distribution of percentages, more than one category. You guys learned in chapter 8 how to deal with two categories, two proportions, P1 and P2, and then compare them whether P1 is greater than P2, P1 is less than P2, etc. This, what we learned in chapter 8, we cannot apply in chapter 10 because we have more than two categories. You have, look here, you have a murder, you have a forcible rape, robbery, and aggravated assaults, 4 categories. So the techniques that we learned in chapter 8 would not work here because the techniques of chapter 8 work only with two samples. And here we have 1, 2, 3, 4. And you've seen in the other examples that I showed you guys that you could have as many categories as you want. So we will not be using a z-test. We will not be using a t-test. We will be using a test called chi-square test. And the chi-square, guys, the chi-square distribution looks like this. It's positive. It can never be below 0. So it's always greater than 0. And it is always skewed to the right. This is called the chi-square distribution. It is always a right-tailed test. And it does have degrees of freedom, which we will learn, just in a little bit about the degrees of freedom. And the total area under the curve, guys, it's always 100%. So that's the total area under the curve. And this distribution is always right skewed. And the shape of the curve, it changes with the degrees of freedom. The degrees of freedom in this section is number of categories minus 1. So if I go back to this example, guys, and tell you count how many categories do you see? 1, 2, 3, 4. So if you need to degrees of freedom to answer a question later, it will be 4 minus 1, which is 3. That's how you find the degrees of freedom. So to share with you some more information about the chi-square distribution, total area under the curve is equal to 1. The chi-square curve starts at 0 on the horizontal axis and extends indefinitely. You can see, guys, it starts at 0 and extends indefinitely. The curve does not touch the x-axis. It's very close, but it doesn't touch, the x-axis. The chi-square curve is right skewed, as I told you. As the number of degrees of freedom become larger, the chi-square curve tend to become like a bell-shaped curve. So if the degrees of freedom, let's say, is 30 or 35 or 40, the shape of the curve is going to become like a symmetric curve. Okay. Now, let's begin with an example. I think I'd like to explain, just the concepts using an example, and then that will make sense to you when you see it in an example there. So we're going to do an example, and let me read the example for you. A teacher figures that the final grades in the chemistry department are distributed as 25% A, 25% get a B, 40% get a C, 5% of the students get a D, and 5% get an F. You suspect that this teacher is not telling the truth, that the distribution of the grades is different from what the teacher's saying. The teacher's saying 25% of his students get an A, 25% gets a B, 40% get a C, only 5% get a D, and 5% get an F, which is a failing grade. So at the end of the randomly selected semester, the following number of grades were recorded. So these are grades from the teacher's records here. Out of 100, I think if you add them up, guys, they will be 160 students. So out of 160 students, this teacher had 42 students earn an A, 36 students earn a B, 60 students earn a C, only 8 students got a D, and 14 students got an F. Test the claim that the distribution for the department is different than expected. So we want to test the claim that the distribution, that's claimed by the teacher is no longer valid. It's different now. So let me show you guys how you state the null in the alternative hypothesis. It's a generic statement. You state this for every single problem. It doesn't change. In HO, guys, you say the distribution is as claimed. Can you guys guess what HA is going to be? What's the opposite?
Is not as claimed?
Is not as claimed or is different than expected. Now, distribution of what here? It's a grades, but I'm just writing the generic statement. Is not as claimed or has changed. Okay. Where is our claim, guys? Is it in the null or the alternative? He says, test the claim that the grade distribution for the department is different than expected. So would it be H2? Which one?
The alternative?
Yes, I agree. Does everyone else agree, guys? If they say it is the same, oh, I'm sorry, you guys, you hear a noise, just I think I have a long service outside. So the distribution is not as claimed, and then the distribution is as claimed. So this is the first step, guys, of the test. And in all the examples that I showed you before, you state the same thing. Distribution is as claimed, distribution is not as claimed. And read the question. If he asks you, check that the claim is still, did not change, is still the same, then your claim will be in HO. If he says, check that the distribution has changed, then your claim will be in HA. And it is HA in this case here. Step number 2, guys, it's going to be the calculation of the test statistic. I'm going to show you how to do this. It's going to take a little bit time. I'm going to do it by hand, and then later we'll learn how to use technology. But I might ask you to show the work, just on a test or in the homework, and how to find the test statistics. So that's why it's very important that you learn how to do this by hand. So I'm going to show you the work. It's tedious work, but it's easy, straightforward. So step number 1 is state HO and HA. Step number 2, calculate the test statistic. And once we are beyond step number 2, we're almost done, guys. And the test statistic, guys, is called chi-squared. So you learned about Z, you learned about T, and now chi-squared, it was the same in 7.5 where I gave you an extra credit assignment there, but it is called chi-squared. So if you want to read it, you read it like chi-squared, like this. Okay, let's see. Let me show you how we're going to find the test statistic. I'm going to create a table here. I'm going to put the categories first there. So you could get a letter grade A, you could get a B, you could get a C, you could get a D, or an F. At the college, we don't have F. It's called E here at Henry Ford College. Those values, guys, that you see right there are called the observed values. These are the values that we got from the teacher's data, from the teacher's record. They are called observed values. So I'm going to call him O here, and I'm going to put him right there. So for A, I got 42 students. B, I got 36 students. Then I got 60 students. Then I got 8 students. And then I got 14 students. So are we good so far, guys? We got the observed values. Now we need to know the expected values. And let me tell you what the expected value, we call it E. And I'll explain what the expected values are. We expect 25% of the students to get an A if the teacher's claim is valid. We expect 25% of the students to get a B. we expect 40% of the students to get a C and so on and so forth. So your expected values, guys, it's going to be the percent of the total always. So we'll begin with A, which is 25%. And if you add those up, guys, you're going to get a total of 160. So your E here, it's going to be 25% of 160. Can someone compute 25% of 160 for me? 0.25 times 160. Okay, what did we
40.
get? 40. I agree. Good. What's your feeling, guys? Do you think the teacher is right so far? The teacher expects 40 of his students to get an A. How many did we get to get an A? Actual. These are the actual, guys. These are the actual, and these are the expected. Well, he seems to be right so far. 40, 42, very close. Not bad. But let's see. We're going to keep going. O observed. O stands for observed values. These are called the observed values. Observe these, the data that you collect. And the expected values are the percentages that they give us. So we expect 25% of students to get a B. So 0.25 times 160, which is 40, and which is still close. So probably the teacher's claim did not change. It's still valid. Okay, what about C, guys? 40% of 160. Can you do that for me? Which is, if you multiply,
64.
exact. Oh, it looks close too. So I'm feeling that I don't think we're going to be able to reject the teacher's claim that it is 25, 25, 40, 5, 5. We'll see. D, 5%. Okay, 5%, guys, 0.05 times 160. That will be 8. Exactly. Wow. And 5% will be 8 again. Okay. It does seem that the expected values are very close to the observed values. If they are very close, guys, it's likely that the distribution did not change and it is as claimed. So the HO is true. If you feel that there are a lot of changes, probably HO is no longer true. And then the distribution has changed. But I have to continue the test just to make sure. So now just watch me, guys, doing the test statistic. There are steps that you have to do to find the test statistics. But I think the most important one was how to find the E's. And I showed you how to find, even if you use your calculator, you need to know how to find the E's, because the calculator will ask you for the observed values and will ask you for the expected values before it runs the test. So we need to know what O and E are. Next step, guys, we need to do O minus E. Okay, 42 minus 40. I'm going to take my time with this, guys, just to see how we're doing this. 36 minus 40. 60 minus 64. 8 minus 8. 14 minus 8. Which is 6. All right. Now, next, guys, we're going to do O minus E squared. I want you to square what you got in this column. So can you guys help me? 2 squared is what? 4. What's negative 4 squared?
16.
16. You get rid of the negative. No more negative signs.
Positive.
It's all positive. Probably you're wondering what am I doing, but I'm just gonna get you to find the test statistic. I got one more step and I will be done. I usually, if I wanted you to show the work, I would provide you with the table like this, And I'll provide, with the headings, and all you need to fill in the blanks, guys, in order to arrive at the test statistic. Okay, one more step, and then I'll tell you what the test statistic is. I want you to take what we did in this column and divide it by the values that we got in E. So this value here that we got in this column, we have to divide it by the value we got from E. That's what it says, O minus E squared divided by E. So that will be 4 divided by what? 40. And what would be the next one? 16 divided by what, guys? Can you tell me? 40. And this one, 16 divided by 64. 0 divided by 8. And 36 divided by 8. And finally, the test statistic, chi-square, is defined to be the sum of the last column, that's the formula for the test statistic. So that's why I did all this work, guys, to arrive at this column and add up the entries in the column there. So your test statistic, guys, will be 4 over 40 plus 16 over 40 plus 16 over 64 plus 0 over 8. I don't need it because it's 0, 36 over 8. And let's do this on the calculator and find the answer. All right, so that would be, just use your calculator, guys, to do it. 4 divided by 40 plus 16 divided by 40 plus 16 divided by 64 plus 36 divided by 8. So it's 5.25. That is called the test statistic. All right. Step number 3, which is, if you're doing it by hand, it is the critical value approach. And let me show you how to do this. You draw the curve. You draw a right skewed curve right there. You put the 0 there. You put the chi-square curve there. And then he says he wants alpha to be 0.01. We go to this table, guys, which is called table 6, the chi-square table. Okay, how many categories do we have here? A, 1, 2, 3, 4, 5. So the degrees of freedom, guys, will be 5 minus 1, which is 4. Okay, watch. And alpha, remember, guys, it's 0.01. So degrees of freedom is 1, 2, 3, 4. And then alpha is 0.01. You can see it right there, guys. And if you look at the value, just read the fourth value, which is 13.277. And because the curve is right skewed, this test, section 10.1, it's always a right tail test. So you always shade areas to the left. And this is your critical value, CV, and they call it in the book chi-square sub-0. And what did I get here using table 6? I forgot. I got 13.277. This is the rejection region. And how did I find this one? Using table 6. Alpha is 0.01 and degrees of freedom is 5 minus 1, which is 4. Okay, guys. So it's always in this section that the right area is the rejected area. This is when we reject the null hypothesis. What was your test statistic? It was 5.25. If I am, guys, to put 5.25 on the number line here, where would I put 5.25? Do I put it to the right of 13 or to the left of 13?
To the left.
To the left. Exactly. Put it anywhere you want, right here. So it's not in the rejection region. The shaded region is the rejection region. So your conclusion is to fail to reject HO. If your value falls in the shaded area on the number line that has the shaded region, then you reject HO. If it doesn't, then you fail to reject HO. And your conclusion is there is not enough evidence at the 0.01 level of significance to conclude or support the claim that the distribution has changed. To support the claim that the distribution of grades for this particular instructor is different than expected.
Professor Bazzi, could you please move it up?
Yep, I can do that. Of course. So there is not enough evidence at the 0.0 level of significance to conclude or to support the claim that the distribution of grades for this particular teacher is different than expected. Meaning, guys, that we think that the teacher's distribution is still valid, and you were able to see that by yourself because you saw the numbers between the difference between the observed and the expected is barely no difference. So that means the distribution is still valid. When you see wide difference between O and E, then you might conclude that the distribution has changed. Okay, just in few minutes, guys, I'm going to show you how I could have done this using the calculator, and then we'll wrap this up. So that should take me just a couple minutes to do this. For the calculator, guys, you need to enter the observed values and you need to enter the expected values. So you need to do the manual work, a percent of the total, and get those numbers for the calculator. So let me show you how we could have used the calculator. So you go to Stat Edit. And you can guess, guys. L1 is going to be for observed. And L2 is going to be for what? Expected. So let's put the observed values. 42, 36, 60, 8. After you see what the calculator does, you're going to say, why did you make us do the test statistic by hand? And now, the next one is 40, 40, 64. This test is called the goodness of fit test, what you're learning, guys, in this section. 8 and 8. It's a goodness of fit test. When you have a distribution of more than 2% percentages, then you use goodness of fit. So let me take it to the test. Stat tests. Scroll up. And can you guys see the test here on the screen? Can you tell me which one is it going to be? From the title of this section.
Or D.
D, and I agree. Let's see what the other student said. D, correct. All right. So it is D, I agree. It's GOF, guys. GOF stands for goodness of fit. And this is chi-square, so don't mix it up with C. C is reserved for section 10.2. This is it. Goodness of fit test. Enter. By the end of the semester, guys, we will have used every single test. There's E, we're going to be using that in section 10.3. And there's H, we will be using that in section 10.4. We don't use G because it's a T interval, not test. So goodness of fit. Okay. Observed values, L1, we're good. Expected values, L2. Well, there's one thing I have to change before I hit calculate. What is it, guys?
Degrees of freedom.
Yeah, what's the degrees of freedom? I have 5 categories. -1, it will be what?
4.
Don't ignore the degrees of freedom, guys. Count how many categories he gives you. 1, 2, 3, 4, 5, and then subtract 1. So if you see a 5 there, it's just probably from a previous question that I did before. And if you want me to do a draw, I can do a draw. Look how it is screwed to the right. You can see that. That's the p-value. You're not getting the critical region here. You're getting the p-value. Okay, you see the test statistic, guys? 5125. That's what I exactly got by hand. And here's the p-value, which is 0.2626, which is bigger than alpha. If the p-value is bigger than alpha, what do you do, guys? You what? Fail to reject the null hypothesis. And then the conclusion will be the same. So the difference between using technology and critical value is step 3. This is called the critical value approach. This is called the p-value approach. That's it for today, guys. You can start working on section 10.1 and then we'll continue the rest on.
Professor Bazzi, so for step 3,